In this video, we'll be talking about solving polynomial and rational inequalities by hand. These are nonlinear inequalities, which make them a little bit different from what you may have seen with linear equations. The big way to do these by hand is to produce something we call a sign chart. Sign there refers to like whether it's positive or negative. So we're going to build a chart. We're going to throw in the signs, and from that we can evaluate the solution set for a nonlinear inequality. We're going to do these by hand. You can do these much faster across the board using electronic tools. I'm going to do by hand in this video and then follow with a couple of electronic tools in a follow-up video. So you can look for that. As far as this goes, I'll just get right into my first example and I'll explain sign chart when I get to it. So I've got x cubed minus 22x is greater than 3x squared minus 24. This is cubic on the left and quadratic on the right. But because we're using a sign chart, well, all we're concerned about is positive and negative. I need one of the sides to be 0. I'm going to always head toward the side of the equation that will make my leading coefficient positive. So since x cubed is positive on the left, I'm going to move everything to the left. So x cubed, I'm going to subtract 3x squared. I already have minus 22x, and I'm going to add the 24, and that leaves me with greater than 0. Part of the reason I like to have the positive leading coefficient is this way I know I'm not going to need to change any signs or multiply by a negative on both sides, which would flip my inequality. You can switch the whole problem. Like if you want to have a positive one that's positive on the right and you want it on the left, just switch the inequality around and that's fine. But here I am on the left. Greater than 0 is what I have. So the whole point of the sign chart is I'm going to produce a chart that tells me where this polynomial is bigger than 0 and where this polynomial is less than 0. Bigger than 0 being positive sign and less than 0 being negative signs. In order to do that, I have to find where it's going to switch, and the place where we switch from being positive to negative is at the zeros. So I'm going to solve this, start off solving this the same way I would with an equation, in that I'm going to try to factor it. Since this is cubic, and I don't see a pattern, factor by grouping is not going to help, and it's not in quadratic form, there's no greatest common factor, I'm going to have to get right into synthetic division. I said by hand, so rather than trying to find the zeros using a calculator or a graphing tool of some kind, I'm going to start right in with synthetic division. I'm going to need factors of 24 for my rational zeros. So I'm going to use synthetic division with 1 here, 24, and give it a try. If this doesn't work, I'll move on to other factors. 1, 1, negative 2, negative 2. Oh, but look at that. First try. So this tells me I've got x minus 1 as a factor, because k there is 1, and x squared minus 2x minus 24. Since this is now quadratic, I can factor this. I need two numbers that multiply to negative 24 that add to negative 2. That'd be negative 6 and positive 4. So there it is factored. Now this whole time it has to be greater than 0. I haven't done anything to change that yet. So this is if you think of this graphically speaking, this is a cubic polynomial, and I'm trying to figure out where it's above the x-axis and where it's below the x-axis. If I graph this, I could see it, but we're trying to avoid using electronic tools here by hand. So I'm going to put these in order instead. The zeros are negative 4, positive 1, and positive 6 when I put them in order, which means I'm breaking the set of all real numbers starting at negative infinity and heading toward positive infinity into different sections. So the first section is all the numbers from negative infinity to negative 4. My second section goes from negative 4 to positive 1, then from 1 to 6, and then from 6 to infinity. So all real numbers are indicated somewhere on this chart. And I've split it into sections. Now the reason I did this at the zeros is these are the only places where our polynomial can switch from positive to negative. So each one of these sections is entirely positive or entirely negative as far as the answer you're going to get. The default way we fill out our sign chart then is we pick a candidate that's somewhere in this interval. So a number between negative infinity and negative 4. I can use negative 5, it's in there. Could use negative 10 or negative 100. Sometimes bigger numbers are actually easier because we don't care what answer we get, really. We care what sign the answer has. So if I stick in negative 5 minus 1 is negative. It's negative 6, but I don't care that it's negative 6. I care that it's negative. If I stick it in here, I'm sticking in negative 5. If I stick in negative 5 here, I'm going to get negative again. And if I stick negative 5 in here, this one will also be negative, which is fairly typical for the leftmost category. All the factors are negative. The negative times a negative times a negative makes a negative. So this polynomial is negative. The answer is negative whenever you stick in a value less than negative 4. You'll get a negative response from this polynomial. In my next section, from negative 4 to 1, I can pick any number in there. 0 is probably going to be the easiest. When I stick 0 in here, it's negative. If I stick 0 in here, negative. But when I stick 0 in here, I get positive. So negative times a positive is positive. Similarly, over here, I'll stick in, say, 2. When I stick 2 in here, 2 minus 1 is positive. 2 minus 6 is still negative. And 2 plus 4 is still positive. So now I have negative. And lastly, if I stick in a number, you could do 7. I'm going to stick in like 100 because 100 minus 1 is clearly positive, as is 100 minus 6, as is 100 plus 4. So positive. This alternating pattern is fairly common. I've been talking in my recent videos a lot about multiplicity because that's one of the key ideas here in pre-calculus as far as simplifying your workload. If you understand multiplicity, each one of these zeros has multiplicity 1. None of them have squares or repeated, the factors aren't repeated, which means every single one of these is a place where the graph crosses the axis and changes sign. So it shouldn't surprise us that the sign changes with each section. In fact, if you find one of these and you pay attention to the multiplicities, you can fill out the rest just by remembering that things with odd multiplicities are sign changes, and if one has an even multiplicity, there's no sign change, and so you'll have 2 sections with the same sign. As far as finishing up, now I have the information I need. I just have to evaluate where is this polynomial bigger than 0, greater than 0. And this section here, where it's positive, is greater than 0. The endpoint, negative 4, is going to be equal to 0. So if this were a loose inequality, if this said or equal to, I could put negative 4 with a bracket, but it's not. So negative 4 gets a parenthesis because it doesn't satisfy my inequality. And all the way up until 1, which again, that would make it equal 0, so not included. This whole section's out because it's less than 0, but the section on the end, 6 to infinity, also included. So this is a sign chart, and it's a way of organizing our thinking and gathering the information reliably to be able to evaluate where it's true. The sign chart, because it only measures positive and negative, will only work if the equation or inequality has 0 on one side. So you need to get everything over to one side. If you're unwilling to get everything over to one side, or you can't for whatever reason, or you can't find the zeros, you're going to need an electronic tool. As far as rational inequalities, the concept is essentially the same, except in addition to zeros, I have to watch out for discontinuities. Because despite what I said about polynomials, if you have a discontinuity in your function, that is a place where your graph can suddenly change signs without actually being 0. A vertical asymptote frequently involves a sign change. Jump discontinuities can change signs. Even a removable discontinuity, if the removable discontinuity is right on the x-axis, can have a sign change without ever actually being 0 in the middle because the 0 is not included in the function. So any discontinuity can produce a sign change, and I'm going to watch out for those. The first step remains the same. Get this all over onto one side. Minus 1 over x plus 5. Now, I would love to be able to just get rid of the fractions. Unfortunately, since this is not an equation, I shouldn't multiply, say, by x on both sides. because I don't know whether x is positive or negative, and so I wouldn't know whether or not to switch the inequality around. So multiplying x on both sides is not a good idea for inequalities. Instead, I am going to have to add these fractions together. I'm going to add these into one bigger fraction, which you may not like as much, but it's what we have to do. So my least common denominator is going to be x times x plus 5. So I need to multiply this fraction by x plus 5 on top and bottom in order to make the same denominator. And I need to multiply this other one by x over x. So that gives me x plus 5 over x times x plus 5 minus x over x times x plus 5. I've forgotten how to write greater than or equal to 0. So when I add these together, then x, or subtract these together, I guess x minus x is 0. 5 is not like terms with them, a like term with them. So as we learned when we learned to graph rational functions, the top of the fraction is going to tell you where the rational function can equal 0. And here we can see there are none. There's no way to make 5 equal 0. So this has no zeros. It does, however, have two discontinuities. Infinite discontinuities at x equals 0 and x equals negative 5. So those are the only divisions I need to make on my sign chart. If I had zeros, I would include those on the list as well. So I'm going to start with negative infinity to negative 5. Then I'm going to have a section from negative 5 to 0, and then from 0 to infinity. So if I pick a candidate, the easiest, zero's right there. So I'll pick like negative 10 over here. I've got a 5 on top. It's positive no matter what I do. X down here will be negative if I stick in like negative 10. And negative 10 plus 5, that will be negative as well. So positive divided by two negatives, that makes a positive because the negatives cancel. In here, I need something like, say, negative 4, which the top will still be positive because it's just 5. But negative 4 and the negative 4 plus 5 will actually be positive, so this section's negative. Although really, it's just as easy to look. See, these are multiplicity 1. So I can predict an alternating sign pattern. There's no squares. In this case, I'm looking for greater than or equal to 0. So negative infinity to negative 5. If this were a 0, I would put a bracket on there because at negative 5, this would equal 0. But since this is a discontinuity, I'm not allowed to stick in negative 5. That gives a divide by 0 problem. So it's not a solution to my inequality, even though it's a loose inequality. And then nothing in here, those are all negative. And then over here, positive, though again, 0 is a vertical asymptote. It's a discontinuity, so it's not a suitable choice for a solution. So it gets a parenthesis. I need an example where I actually use a bracket. Fortunately, I have just such a one. Negative 3 times x minus 3. In the interest of time, I have already factored this one for you. X plus 2, x minus 5. Less than or equal to 0. So this one I've already factored, just to keep an eye on it. Now, the negative 3 is never going to be 0. X minus 3, that gives me a 0 at x equals 3 with multiplicity 2, which is going to come up when I fill up my sign chart, because I'm not going to have an alternating sign there. It'll be the same sign on both sides. Then I have vertical asymptotes at x equals negative 2 and at x equals positive 5. So when I build my sign chart, negative infinity to negative 2, negative 2 to positive 3, 3 to 5, and 5 to infinity are my sections. I'm going to start way over here on the left, stick in something like negative 100. This is positive. This will be negative when I stick in negative 100, but because I'm squaring it, it'll wind up being positive. So the top will have a negative times a positive. And on the bottom, if I stick in like negative 100, these will both be negative. So that's 3 negatives total. This is a negative section right here. In the middle, alternate, right, multiplicity. So this gap here is produced by this vertical asymptote from this factor. It's got multiplicity 1, so there is a sign change there. Whereas this one here, 3, is produced by the one that has multiplicity 2. There's no sign change there. And lastly, as I move across here, this vertical asymptote produces a sign change, so negative over there as well. Which means my solutions are negative infinity to negative 2. Negative 2 is not a suitable candidate because it's vertical asymptote. Now here, there's actually a tricky bit right here. Because this is a loose inequality and 3 is a 0, 3 is going to make this inequality true. But it's surrounded by positive answers. So it gets brackets, but it's in the brackets all by itself because it's the left and right side of its interval. And then the last section, 5, is a discontinuity. It's not a suitable answer. And then we go to infinity. So you can see 3 gets brackets because it's included. It's one of the numbers to the solution, whereas 5 and negative 2 aren't. All right. I have actually 2 more to show you briefly because they have rather odd solution sets, which is the sort of thing that can happen with nonlinear inequalities. Here I've got a quadratic. As I'm trying to factor this, I see I need 2 numbers that multiply to 3 that add to 2, which is problematic because 3 is prime and 3 and 1 is 4. Negative 3 and negative 1 is negative 4. So quadratic formula tells me opposite of 2 plus or minus the square root. B squared is 4, and 4ac, 4 times 1 times 3 is 12. This is going to produce a negative in my square root, which means the zeros for this are imaginary. They're not real. And since the zeros are imaginary, there are no sign changes for this polynomial. If you want to talk about this graphically, this is a parabola that opens up. It never drops below the axis. It has no x-intercepts. So this parabola is always either positive or negative. Its sign chart, if you were going to make one, is this. Negative infinity to positive infinity. It's always the same sign. All I have to do is figure out which sign. So if I stick in 0, I get 3. This is always positive, which means when is it less than or equal to 0? Never. This has no solution, which you can write out in words and everybody will understand it. If you want to be fancy, you can use the null set, which you can write this way or this way. And nobody should complain at you about those either. The other weird example I have for you is this one. X squared plus 12x plus 36 is greater than 0. In this case, when I do this, I'll get x plus 6 squared because the 2 numbers that multiply to 36 that add to 12 are 6 and 6. So again, this sign chart is a little weird. It's negative infinity to negative 6 and negative 6 to infinity, which I hardly need to draw. But if I do, if I stick in a very negative number, I'll get negative squared, which is positive. And if I stick in a very positive number, I'll get positive squared, which is positive. Note, this is multiplicity 2, no sign change, not surprising. So this graph is positive nowhere. This graph is never greater than, I'm sorry, always. This graph is always greater than 0. So positive and positive. The problem is here at 6, it's not actually greater than 0. Because at negative 6, it will be equal to 0. So my solution is both of these intervals, just with 6 not included. So again, parentheses. And if I wanted to indicate the reverse of this, if this instead had less than or equal to 0, then the only solution would be 6 itself, which you can write as a number in its own brackets set notation. If you want to write that in interval notation, that's just 6, also fine. So this one has exactly one number in its solution set. This one has none, although clearly you can have a solution. You could have a solution. If this were plus 37, you'd have a situation where all real numbers is the solution set. Hopefully that helps you out. Remember to do these by hand. We want to make a sign chart. Frequently, for things that are easy to factor, it may actually be faster than producing a graphical solution anyway.